Hi everyone, welcome to the white paper series. So this week's white paper is training compute optimal large language models. We have seen that this paper has come out by DeepMind and this paper came out around 2022. We saw the Kaplan scaling laws in 2020 by OpenAI. Now this is something around scaling. This paper does not introduce a new architecture. This paper does not talk about a new idea of a transformer. This paper does not talk about one specific type of data set, that is going to solve all the problems. So let's try to discuss in detail what this paper is going to talk about and what are we going to learn. So this paper fundamentally questioned everything around training. So the paper kind of questioned, are we training or were we training large language models the wrong way, right? Did we have an efficient pathway to train the large language models? So the main objective is, so for years and years, the AI researchers and the AI engineers have trained large language models inefficiently. This paper questioned the idea that they were training on. And what was the precise question that they made? So they were like, the GPT-3 that came out recently, it had billions of parameters in its model capacity. So they were like, is the model really undertrained or do we need that much of parameters, right? So to understand the whole landscape that is going to come in the further video, we have to understand that this paper talks about three paradigms, right, or three parameters a lot. The first parameter that it talks about is compute, right? Largely the whole compute parameter or the compute dimension is fixed for the whole paper. Fixed means we don't vary a lot of compute, right? Because compute is a constraint that is, that acts as a bottleneck for the organization. Compute is a constraint from the top down leadership decision that, this is the amount of compute that we have and this is, what we are going to use at max, right? So compute is kind of a fixed axis of scaling. The other variable, the other dimension, that also is part of scaling is model capacity, model parameters, right? So what is model capacity or model parameters? So it's basically the number of parameters a model has, right? So y is equal to mx plus c. A simple model has two parameters, m and c, right? So we can have n number of parameters, right? Along with that, GPT-3 that came out at that particular time in 2022 when this paper was out came out with 175 billion parameters, right? So we were jumping from 1 billion to 10 billion to 13 billion to directly 175 billion, right? So the bigger notion was bigger is better, right? More parameters, bigger model, better performance, right? So we want to see, do we need these many parameters, right? Although we are capped at compute, but do we need these many parameters? And do we just blindly keep on inflating the number of parameters and increasing the model complexity, right? So this is one of the dimensions that it captured. The other parameter that it talks about a lot is the training data, right? That is also a parameter, right? More training data, possibly better performance, right? Let's denote the model parameters by the number n, and let's denote the model's input training data as d, right? So similarly, we have compute is definitely capped and is denoted by c. So these are the three parameters that we will talk about: c, n, and d, right? Compute and model parameters and training data, these three parameters. So for all these years, especially till 2022, we had been training the neural networks wrong because we only kept with the paradigm that bigger models are better, right? So there is a possibility that GPT-3 might also have been trained incorrectly, and some people can question that it was undertrained, right? So for years, the AI industry believed that to build better language models and to build neural large language models, we simply need to make them bigger. More parameters will lead to better intelligence, right? Okay. So the bigger is better paradigm kind of was questioned by DeepMind, and they wanted to question it by conducting a series of experiments, not only question it in a theoretical way, right? So in 2022, these researchers at DeepMind published a paper, which is this one, the one that we're reading. So this paper challenged the whole belief. This paper is formally called as training compute optimal large language models, right? But it is often referred to as Chinchilla paper. So formal name and informal name, right? Both are very famous. Training compute optimal large language models and the Chinchilla paper. So this paper showed that many large language models, including GPT-3 style models, were massively undertrained. We will understand the whole definition of undertraining. And we had too many parameters. when it comes to large models. So you have to understand one thing. Whenever we say large models, there is one specific thing that we are pointing to. Obviously, large models would undertake a lot of compute, it would undertake a lot of training data, right? But whenever we specifically say it's a large neural network, it's a very large model, we are trying to focus the largeness of on the amount of parameters the model is having, right? So what are model parameters? So we have seen the idea of weights, biases in a neural network. We have seen the idea of weights and biases in simple linear models. So all of these weights and biases that are trainable, right, whether it is a neural network or a transformer, all of these are interchangeably called as parameters, right? So more the model parameters, bigger the model, more complex the model, right? Model complexity is also correlated with the number of parameters in the model, right? So more capacity of the model can store more weights, right? More size of the model. So all of these things point to one thing, which is a bigger model. That's it, right? So bigger is not an abstraction. Big does not mean an abstract idea. Big genuinely refers to model parameters, the count of number of parameters. A 175 billion model is a really big billion parameter model, right? And the number of how big it is, 175 billion, right? That's how we denote the model capacity by, right? Model capacity, model size, model parameter, model complexity, all of these things depend on the parameter count, right? And especially the parameter count that is storing all the training memory. I mean, when you train a lot of data, your parameters and weights produce some representation and learn those representation of the training data. That is your model parameter. Now we have to understand one thing, that model parameter, we've completely understood what exactly is it. The other thing that we have to understand is the budget on compute. All the frontier AI companies, they had a strict bar, a strict budget on the compute. So compute was constrained, right? Training large language models is definitely limited by compute. Even today, right? We have three axes of scaling, right? The training data, the model parameter, and the compute. So we have to fixate, for all of these experiments that are done in the paper, we have to fixate compute, and we have to produce experiments on the other two parameters, right? So we also have a notion where compute is a function of, or compute is approximated by, number of parameters and the training data, right? So n here is number of parameters and d here is the training data. So I mean, it's sort of equation. The total compute that we have to anticipate or that we have to approximate is 6 times n times d, right? So these are the three parameters. So we have fixated the compute budget for all the experiments that we are going to do. We're going to do 4 to 5 experiments in this paper, right? So we know that compute is a function of number of parameters and data, right? So but let's fixate compute and see what to tune up and what to tune down. So what to tune up and what to tune down means we're constantly blindingly till now increasing the number of parameters, right, in the model. Now we might question, should we decrease the parameters? But if we decrease the parameter, what is it that we should increase? So we decrease the parameter, and should we increase the training data, or should we do the vice versa, right? Or do we figure out a way to find optimal balance, right? So we are going to start, with all of these experiments. So now while we start with the experiments, what is the trade-off that we will solve for, right? Compute is fixed, right? We know that for the whole paper that OpenAI produced, compute is fixed. So if compute is fixed, right, it has a bar. What we can tune up or tune down is number of parameters in our model and number of tokens in our training data, right? Training data is quantified by number of tokens, not by GBs or petabytes or zettabytes, right? By number of tokens. Parameters is quantified by number of parameters, or model complexity or model capacity is quantified by number of parameters, right? So both of them are usually in billions and trillions, right? Because they are massive in number. Now the idea is, the choice can somehow look like this: should we go ahead with a bigger model, right? Or should we go ahead with more tokens in the training data so that we don't qualify as an undertrained model, right? So is bigger model a better trade-off when compute is fixed, or is more training tokens a better trade-off, right, when compute is fixed? So we have to figure out what is the fundamental trade-off between both of them, what to increase and what to decrease, and with what number, with what ballpark number, right? So the big question that we have to answer is, if we fix the compute budget, how should we allocate? A huge model plus little training data, or a smaller model with massive training data, right? So huge model, with bigger training data or smaller model with massive data, right? So this is the central question that this Chinchilla paper is going to answer. The previous beliefs that have come from earlier scaling laws for neural language models, which have come from OpenAI, the Kaplan scaling laws, that increasing the model size gives the largest amount of gains. This has been the huge perception or thought or belief, and we have also seen a lot of experiments around it, but this assumption is now being challenged, right? So the core idea behind the kind of experiments that we are going to produce is that we have to systematically vary the model size and the dataset size, right? And we have to measure training loss and validation loss. So we want to discover a combination of these parameters and trade-offs that gives the best performance for a fixed compute budget, right? What is the trade-off among both of these scaling axes? Compute scaling axis is fixed. Model size and data set size is what we are going to trade, tune up or down. What is the best trade-off, right? We will see that when we fix compute and when we train many models of different sizes, right? So this is the first experiment. If we train many models of different sizes, what we are going to observe is that, let's say that we have 70 million tokens model and we have 300 million tokens, we have 1 billion tokens, and we have 10 billion tokens, and we have 70 billion tokens, right? We are training these models of different sizes, right, from 0.07 billion to a billion to maybe 100 billion, and we are measuring loss versus model size. How is loss being affected, with respect to model size? We will see that the loss keeps on decreasing as the model size keeps on increasing, right? This is the first experiment. So this kind of matches our existing scaling laws, that loss will decrease as you increase the model size. The second experiment that we are going to observe is around the data, right? So first was around model capacity, second is around the data. That when we say data, how do we quantify it? We quantify data with the amount of tokens or training tokens, as I like to say, and this is also in billion. Let's say we have 10 billion input training tokens, 50 billion input training tokens, 100 billion tokens, 500 billion tokens. The observation against loss is that, will the loss decrease if I increase my training token, or will the loss increase, or will the loss stay static, right? We will see that the loss keeps on decreasing as you increase the amount of data in your training tokens, right? Now, this is also very naively understood that if you increase the training data, obviously you're going to, see that decrease in loss, right? So the key insight that we have to find is, how do we combine these two, right? At this point, we can realize that bigger models are helping reducing the loss, or hence increasing the performance. Bigger training tokens or more training tokens are helping reducing the loss or increasing the performance. More is merrier, bigger is better, right? But compute is limited, right? If I increase both of them, if I increase the model complexity, if I increase the training data, my compute will increase proportionately, right? Or even non-linearly, because compute is a multiplicative, effort of number of parameters and of number of training tokens. So if I multiply them, then compute will increase, right? So I cannot increase both of them, right? Because if I increase both of them, compute will non-linearly increase. I have to fix, compute. So if I have to fix compute, I have to tune them up or down, right? So the first two experiments have shown that model size and data set size, or especially the increase in model size and data set size, will increase in performance or will improve performance. I want to find the optimal balance, right? So the brute force approach in the past have been to blindly increase the model capacity, right? We have seen it with the whole GPT family models that have come out, right? So we now introduce something apart from Kaplan scaling laws, which is Chinchilla scaling law. Previously we had Kaplan scaling laws, now we have Chinchilla scaling laws, right? So now we are going to discover the third experiment, right, which is the compute optimal frontier, which will see that, which will show a couple of findings, right? So we have to understand that, the first two experiments were super naive and super trivial. The first two experiments noted that in, keep the model bigger, keep training data more and more, right? So more training tokens, bigger model capacity, right? But obviously cannot do that, right? That is super trivial, that is very brute force, right? So we have to distribute compute between them, we don't have to proportionately increase everything, right? So what is going to be the compute optimal experiment? So for a fixed compute budget, which combination of parameters and tokens produces the lowest loss, right? We have to find out such a combination where the loss is decreasing, the performance is increasing, the loss is decreasing, and that is the optimal balance between both of them, right? So let's say that they conducted an experiment where on one axis we had model parameters, on another axis we had validation loss, right? So now we try to plot. So we see plots like 10 billion tokens and 50 billion tokens and 100 billion tokens and 300 billion tokens and 1 trillion tokens, right? So we saw that if I train models of increasing size with this amount of data, yeah. So the graph basically talks about plotting everything, keeping the compute fixed and plotting everything like the number of training flops and the model size and the number of training tokens and figuring out what is going to be the lowest training loss. Now let's look at the graph from the paper. Now the graph is divided into three parts, right? First thing is we can see the training loss that is coming down. So the leftmost panel, we can see that the training loss is plotted against compute. Lots of experiments have been done. The x-axis is showing the training compute, the number of flops, and the y-axis is showing the training loss or the horizontal axis. So each colored curve represents a different model size, right? So the dark colors are small models and the bright colors are bigger models, right? As we can see. So what's happening here is the loss is decreasing as we spend more compute training this model, right? So if I train a small model longer, the loss keeps decreasing. If I train a large model, it starts better, but it may plateau earlier, right? Depending on how much data we have fed, right? So this is the kind of analogy that we can think about. Now, the middle panel basically talks about what can be the model size and how does it depend, how does it vary with compute, right? So on the vertical axis we have the model size or the number of parameters. Horizontal axis we have something known as compute, right? Now what's happening is that the gray dots are extracted from the most optimal points, right? And the red dashed line is showing that we are fitting the scaling law, because as we are increasing the model size and as we are increasing the compute, we are able to increase the performance, right? But what we have seen is the as compute increases, the optimal model size also increases. So the optimal model size here is denoted by the green dashed annotation, which is the 67 billion, right? So on the right side we see a vertical line that represents that is representing the compute used to train, right? So at this particular compute budget, the optimal model size that is predicted by Chinchilla scaling law is 67 billion, right? So which means 67 billion parameters. So if you had this compute budget, the best model size would be about 67 billion parameters, right? And what would be the optimal number of training tokens is demonstrated on the rightmost graph, right? On the rightmost graph, we can see that we have compute, right, ranging from 10 raised to the power 17 flops to 10 to the power 25, and we have number of training tokens, right? So training tokens go till 10 to the power 12 training tokens. Now what's happening is we are trying to understand or predict the optimal tokens, right? So we can see that as compute increases, we see that the amount of training data is also being increased, but the optimal point of training tokens is 1.5 trillion, right? We also see that infinitely increasing the number of parameters and infinitely increasing the number of training tokens also plateau in performance, right? I cannot blindly keep on increasing, right, and expect that the performance of the model is always going to increase, right? There can be a plateau, right? That generally happens. That's why we are trying to find the optimal trade-off, right? How do we proportionally increase compute and how do we proportionally increase the number of parameters and training tokens, right? So we fix compute and how do we proportionally increase the number of parameters and number of training tokens, right? So the takeaway from this graph is basically that loss decreases with the with increasing compute, and the performance of the model increases with the number of parameters, but there is an optimal number of parameters for this particular compute when we fix that compute, which is 67 billion, and 1.5 training tokens is the optimal for this particular model, which is 67 billion. And we can probably try to predict what is the relation between number of parameters and number of training tokens, right? And we can formulate a scaling law, right, around it. So in the further part of the video we are going to observe that we were going to derive the whole Chinchilla scaling law, which is there a scaling law that tells us exactly how much data we should use for a given model size, right? So basically the relationship between n and d, since compute is fixed, right? So how do we fit the scaling relationship? So the relationship is approximated and is a linear relationship. So the optimal number of training tokens is 20 times n, or 20 times the model parameters. So if you have a model size of 1 billion parameters, 20 billion tokens is the optimal tokens which used for training. If you have 10 billion parameters, 200 billion tokens is the optimal training tokens. If you have 70 billion parameters, 1.4 trillion tokens, right, or close to 1.5 trillion tokens, right, is the number of optimal training tokens. So we must increase the number of data or the number of training tokens and the model size proportionally, right, and together. So this is what the Chinchilla scaling laws say, right? And they exhibit a linear relationship between n and d, right? So the last experiment is to validate the scaling law. The researchers kind of trained a new model known as Chinchilla, the DeepMind language model. So its configuration followed the new compute optimal rule, right? So it had approximately 70 billion parameters, right? It had approximately 70 billion parameters, and the training tokens were used as 1.4 trillion, right? So the comparison and the result was that despite being the model much smaller when compared to GPT-3, right, which was 175 billion, or Gopher, which was $280 billion, 280 billion parameters, which was also part of this experiment. So, and GPT-3 and Gopher, both of them showed that the 70 billion parameter model, although it is very small, right, but when it is fed 1.4 trillion training tokens, the Chinchilla model achieved better performance than these large models, right? So the compute efficiency matters more than the raw model size, and the training data, the number of training tokens matter, than simply increasing the model capacity or model size, right? That is why the paper kind of said that you will balloon or saturate at increasing the performance. We will saturate at the performance if you keep on increasing the parameter size infinitely. And that's why they claimed, or they said and gave an opinion, that GPT-3 might be an undertrained model, because the kind of parameters and the kind of training tokens it has, the relationship is skewed towards the model size, right? The ratio should have been 1 is to 20, right? So you should have 20 times more training tokens in your parameter count, right? This is what they kind of claimed, right? So the conceptual breakthrough was, so bigger models tend to move towards bigger intelligence, but the dominant metric for progress was parameter count so far. But the Chinchilla language model shows that the training data is also a significant parameter. The assumption that scaling model size alone would continue improving performance is false, right? Or will have saturation. Instead of focusing on maximizing the parameters, the paper kind of reframed to maximize performance for a fixed compute budget, and use both the parameters efficiently. The first parameter is the number of parameters in the model, and the second parameter is the training tokens, right? So the Chinchilla paper influenced every model that followed after it, right? So for example, Palm from Google had 540 billion parameters and close to 800 billion training tokens, right? So this configuration still leaned somewhat toward the earlier scaling philosophy, but it also reflected growing awareness in increasing the number of training tokens, right? So it was not 20x, it was close to 2x, but they still kind of indexed on this particular idea that came out from Chinchilla. So the training cost is obviously a one-time expense. The inference cost is a recurring expense, right? So the observation led them to intentionally overtrain smaller models, right? So for instance, let's say a 7 billion parameter model might be trained on trillions of tokens, right? But the smaller models are dramatically cheaper to train and cheaper to run during inference, right? So even if training cost increase, but the lifetime recurring annual cost of the model decreases significantly. This is the kind of economics that was also discovered. Now what about the idea behind data wall, right? So we have heard this concept of data wall. So the major insight from Chinchilla paper was that the concept which was known as data wall. So the scaling law suggested that optimal training requires roughly 20 tokens per parameter, right? So this has profound implications for future models, which is 10 trillion parameters, right? Consider a hypothetical model might require 200 trillion tokens, right? So according to this particular law of very very high quality training data. So finding this amount of clean, non-redundant, non-repetitive data for training, right? For one single model by a company is very difficult, right? So this can be a bottleneck. Finding the huge amount of training tokens can be a bottleneck, right? So data availability can be a bottleneck. That's why we might hit a data wall. They used to say that we have hit a data wall, we might hit a data wall. So the realization had already triggered, that this realization had already triggered, more and more avenues like data deduplication, synthetic data generation, reinforcement learning from AI, right? All of these approaches kind of aimed to extend the available data supply, right? So the last part which I can maybe talk about is from this paper, is that this paper is nothing but a guide to resource allocation. Let's say if we have a fixed budget and we want to train a large model, so the budget is measured in GPU hours and dollars and electricity consumption. So our objective is to stay on the Pareto frontier of the model performance. So in simple words, we have to maximize the model quality for a fixed compute budget, right? And so if we have to figure out a trade-off between model capacity and the training signal diversity, right? So we have to consider two extreme cases: whether we do a very large model on a small data set, right? So this is the first case. So in this scenario, the model has enormous capacity but very little data. That's why we call it undertrained model, right? Under leveraged model. Many parameters will run redundant patterns. They will tend to overfit. They will tend to memorize things, right? The representation that they produce might be a little poor, and it's not the best generalization over training data, right? So it's wasted model capacity. The other case is very small model, massive data set. Now this is the opposite situation. So eventually the model will saturate, right? So it's the model will saturate means the model will not be able to produce the best representation and keep on learning that. So it simply does not have internal capacity or parameters to learn that representation that is produced from this training data. So the chinchilla point, the optimal point, the middleware, right? So this is basically that you should aim to have the training tokens as 20 times your number of parameters, right? So whichever d is close to 20 times your n, right? So here if d is close to 20 times her n, so you will see that the compute is order of n square, right? So compute will have an order of n square relationship with the number of parameters. Okay, I think this is a good enough explanation of what the paper produced and what the paper introduced, and how we have been using the Kaplan scaling laws and the Chinchilla scaling laws, you know, to look at our training and inference methodology while coming up with a new model. Thank you. I hope this was useful. I will see you in the next video.